Welcome to module 57 of Database Management Systems course in the IIT Madras online BSc program. In the last module, we started discussing about query processing and defined the measures of query cost, primarily in terms of disk transfers and disk sake. And then we studied a few algorithms for processing of variety of selection operations, sorting, join operations and few other operations like duplicate removal, projection and aggregation and so on. In this module, we will try to understand the basic issues of optimizing the queries and how a relational expression can be transformed to create alternates for optimization and a correct and not all of them will have to be correct, and a best cost wise best query evaluation plan can be chosen. So, we talk about these two. So, just to look at the query optimization, this is these are the two basic steps that you generate. Once the translation has happened, you have a relational expression. You generate equivalent expressions and use different algorithms for each operation in those equivalent expressions, and then you evaluate them for cost and choose the best one. So, these expressions are now shown in terms of a tree structure. So, what you can easily see that what it is doing is it is making first a join of teachers and course, then a join with instructor, then doing a selection based on department name is same as music, and then finally making a projection of name and title. So, you can very easily read what will this query give is it will give us the name of the instructor and the course that he or she is teaching in for music department, nothing else, right. It is all. Now, this is in simple terms how you will probably write the query or probably how this first translation will happen. But then we can see that well in the final result, the name and title of the instructor, name of the instructor that will come, necessarily that instructor has to belong to the music department, right. So, there is no point treating all other instructors who are not from music department in this whole process. So, instead of doing this filter here, we can do it right below here. What is the advantage? Advantage is a number of total instructors will be many, and they are teaching a lot of courses, all this will, but once you just consider on the music department, there will be few instructors. So, this relation becomes much smaller compared to this relation, and therefore, the subsequent join that you do here would be much smaller as well, and you will benefit in terms of the terms of the operations that you have to do, and finally, you do the projection. So, this is just an illustrative example to make you understand that how a simple equivalent transformation can give you a better way to evaluate a query. So, this is once this is fully worked out, then it is made into an annotated query tree, which is called the evaluation plan. So, we are talking about a little variant of the earlier query, where you want to find the names of the instructors and the courses they have taught in the year 2019, where the instructor belongs to the music department. Right. So, you have two conditions here, and naturally three relations are involved. Instructor has instructor information, courses have course information, and teachers relates instructor with the course who is teaching what. Right. So, you need to join all these three, this part you understand. Now, how can this get optimized? As we had noticed earlier, that department is specific for instructor. So, instead of doing the join and then taking out tuples which has department as music, we can only take those instructors who belong to the music department. So, we do it here. We first take out the instructors with the music department, and for the evaluation plan we are also specifying what is the algorithm. Now, what is the algorithm? The algorithm is use index 1. Why use index 1? I mean that some index on this, because instructor is more or less a static data. Okay. So, it is easy to build the index, it is not going to change very often, and it will give you a very fast selection possible, as we have seen, right, in terms of the selection algorithms we saw in the last module. For the other condition, ER is specific to teaching, right. The courses are again persistent, but the teaching for a particular year is dependent in the teachers relation only. So, we can also make the teachers relation smaller, but in the absence of an index we will use a linear scan for doing that. So, that is the advice to the evaluation engine, right. That is how it is becoming an evaluation plan. It is just not a representation of the query expression or the relational expression. So, then you join these two first, which is for which they use some merge join algorithm, which is better than the kind of algorithms we have seen. You can read up specifically how merge join is done, but this is how it will. And then it joins the last relation course using a hash join. I mean there is specific reasons of why you use hash join at this particular point, because it is easy to hash the courses in a very compact form, because they have unique IDs to deal with. And finally, you do the projection, and here what is being highlighted, that you have to sort to remove duplicates, right. So, this entire thing, this entire tree with these annotations of algorithms is your evaluation plan, and that is what the optimizer has to generate and pass on to the evaluation engine. And naturally, this will be generated based on different alternates that you can have. So, here I mean I just use certain heuristic information, like department occurs only in instructor. So, I can do that selection first, or year is specific to teachers. So, I can do that filter first and so on, but in general the system will have to have a strategy of exploring alternates and choosing the best one based on the cost estimates, which are statistical in nature. So, the cost difference between evaluation plans for a query can be enormous, I mean from seconds versus days and so on. So, the cost based query optimization, where we will have to first generate the alternates. So, how do you generate the alternates? So, we will define some equivalence rules for different operations of relational algebra, so that using those equivalence rules you can convert one expression into another equivalent expression. Then you will have to annotate the resultant expression to get alternative query plans, right, because I mean once you have alternate expressions, you will know what is the order in which these expressions will have to be evaluated, what are the possible available index and so on. So, what is the algorithm that you can choose and so on, and then choose the cheapest of these plans based on the estimated cost. Cost estimate could be statistical information about relation, it could be based on estimation on intermediate results, cost formula for algorithms computed using statistics and so on. So, all these different kind of statistical information will be used to tune your optimize. So, you can see that the same database design, the same query, in case of two very different kinds of data, for example, even the academic data, if you do this the same query, if you run for one university and if you run for a different university, you may get a completely different optimization in terms of the evaluation plan. So, let us see what are these transformational equivalence rules, because we will have to do that. So, two relational algebra expressions are called equivalent if the two expressions generate the same set of tuples on all legal database instances, right. Only then they will be equivalent, that if they always generate the same output for every legal database instance, right. This term is important. Now, here do keep in mind that the order of tuples in a relation in general is not important. So, order of tuples could be different, it is a set, if they are same set, then we accept them. Also, we would not care, we do not care if different results are generated for databases that violate the integrity constraint. If the database violates the integrity constraint, then it is possible that two expressions are equivalent, but generate different results. So, in SQL everything is a multi-set of tuple, right. So, two expression in the multi-set version is said to be equivalent if two expression generate the same multi-set of tuple on every legal database instance. So, which is a little more tricky, because in relational algebra we saw it is a set that we generate. In SQL there could be identical tuples existing in the same relation, because it is a multi-set. So, such identical tuples, occurrences of such identical tuples will also have to be same between the two equivalent expression for every legal instance of the data, right. So, equivalence rules are formed which say how two expressions are equivalent by treating each and every operation one by one. So, these are very intuitively easy rules, but still if you have doubts, you should work it out, think over. For example, if I have conjunction of two conditions, then it is applying the two conditions one after the other, right, which may be easier to evaluate. The selection is commutative. That is, if I have two conditions, then I can change their order, which is very easy to prove, because this ANDing is commutative. So, this is equivalent to theta 2 and theta 1. And if I do that, then by this rule I can say that this is same as this, right. So, all of these are equivalent. The only last in a sequence of projection matters, because if you are projecting, then that column will have to exist in the relation, right. So, if you are making multiple projections, you are basically reducing the number of columns. So, it is a final one that matters, everything else can be ignored, right. These are the equivalent rules. The selection combined with Cartesian product and theta join. So, if you do a Cartesian product and then do a selection by theta, it is same as the theta join, that basically is the definition. And if you have two conditions, that is, if you are doing a theta join and then do a selection, you can combine these two conditions into the same theta join, right. So, these are these are very intuitively clear equivalences, but we are just noting them down. For a theta join and natural join, they are commutative, that is, I can change the order of the relations, which one will be outer, which one will be inner, that can be easily changed. Natural join is associative, that if there are three to be joined, I can do the first two and join the third with the result, or I can join the second and third and join first with that result. Theta join has some nuances in the associativity. For example, if you do a theta join here and another theta join here with these conditions, then you can have that theta 1 and theta 3 ANDed, and you do a theta 2 join with this, right. Think over it, but you will see that this is possible where theta 2 involves attributes of E2 and E3 only. If it does not, then you cannot do this kind of a equivalence, right. So, often it becomes more comprehensible if you draw them in terms of the expression tree, like the way we said the commutativity of theta join, this is associativity of natural join, and this is the last rule that we saw. You can draw them in terms of this tree for easier understanding. Okay, some more the selection operation will distribute over theta join. So, selection operation distributes over theta join in a way that you can do the selection on the first relation and then do the theta joint with the second, right. It is quite obvious. When theta 1 involves only attributes of E 1 and theta 2 involves only attributes of E 2, then in this condition you can distribute the selection on both of them individually. These are all, I mean, you can mathematically prove, you can write down the calculus, predicate calculus formula corresponding to this and show that they are equivalent, but they are intuitively absolutely clear, but keep in mind the different conditions that hold for these equivalences. Projection operation distributes over theta join. How? You are projecting, you have made a theta join and then you are projecting on, say, attributes L 1 union L 2, where the theta, the condition involves only these attributes, it does not involve other attributes. It could, but if it does not, then it is enough to project the first one on L 1, second one on L 2 and then do the theta join. Naturally, this will get smaller, it is easy to see why they are equivalent. So, L 1, L 2 the set of attributes from E 1 and E 2 respectively. Now, let us say L 3 be attributes of E 1 that are involved in theta, but not in L 1 union L 2. Some more attributes of E 1 are involved in the theta, and L 4 are some more attributes of E 2 that are also involved in theta, but not in this union set. Now, what will this look like? Now, since for if L 3 comes from E 1, your projection cannot only be on L 1, it will have to be on L 1 union L 3, because otherwise you will not be able to apply the theta join later on, because you will miss those attributes. Similarly, this will have to be on L 2 union L 4, because otherwise the attributes L 4 will not be available for evaluating the theta. So, once you have done that, you have L 1 union L 3, union L 2, union L 4, all of this. So, you have to then do a projection, but obviously these projections might significantly reduce the size of the relation, because you are stripping off all other attributes. Set operations are commutative, union and intersection, not the difference, as you know, A minus B is not same as B minus A. Set union and intersections are associative, again that is well known. The selection operation distributes over. So, if you do a selection of E 1 difference E 2, you can do that by selecting this and by selecting this, right. And same thing will apply for union and intersection also. Actually, particularly what you can do is, you may not do this selection either, you can just use the same relation, because you are doing a difference, you are going to take away, right. So, whether you do the selection, second selection or not is a matter of choice, all of these are equivalent, right. If you do projection, that distributes over union, right. If you do a projection on the union, it is okay to do projections and then take the union, it is quite simple to understand. So, I will leave a few as exercise for drawing the equivalence rules. For example, create the equivalence rules for group by or for aggregation operations, so that you can generate the alternates, or for say left outer join operation and so on. Now, so what we have now, we have a lot of different alternates that can be generated, right. So, using these equivalence rules. So, let us see the effect on some of our examples that we are seeing. So, find all instructors names in the music department along with the title of the course that they teach, what we considered before, right. Now, this is, we say, is in the course we need course ID to join it with teachers, right, that is a common. We need title at the end in the output. So, rest of the course details can be dropped. Then you join with teachers, join with instructor, select based on department name music, and finally do the projection. But you can use rule 7a, which while doing a selection on natural join, you can restrict the selection to the first relation only. So, by that you move that in here, and this rule is what is being applied, and with this it will get even more smaller. Performing the selection as early as possible reduces the size of the relation to be joined, very basic thumb rule. So, this is pushing relation is a very good idea. You may need multiple transformations. The other query, find the names of all instructors in the music department who have taught a course in 2009 along with the titles of the course that they taught, right, we saw this. So, this remains same. Here you have two conditions and it, right, conjunction of conditions. So, as we have that, we can use rule 6a to change the associativity of the join. So, if we change that, then instead of doing this join first, we are doing this join first. Now, if we are doing this join, we do not we then do the second join. Now, again we can perform the selection first rule, as we have seen, we can push the selection. So, instead of doing the selection on this entire join, we can simply push this on the first relation, which is the join of instructor and teachers, and then join with the this. As we push that, then we have those rules which tell us that I can just do selection based on music on that condition on instructor, because it does not involve any attribute of teachers. Similarly, I can do the selection for ER is equal to 2009 only on the teachers, because it does not involve any attribute from the instructor, right. So, that results in both of these relations first performing a selection, making the set really small, and then doing the subsequent join. So, in the this was a original tree, it was doing a first join here, second join here, then the selection, then the projection. Now, what you are doing? You have pushed this down. So, you are doing a selection on the instructor, you are doing a selection on the year, then doing this join, you have changed by the associativity rule, and then joining by the course and doing the name title. Actually, what you can further do is you can have course ID, title, you can do a projection on the course also. You do not lose any data, it will become even smaller, right. So, some more examples. I think you have we have already discussed this, but it is performing projection as early as possible. We are trying to illustrate that rule, just go through it and you should understand it easily. In terms of join, you use the associativity based on which part is expected to be smaller, right. So, you do that part because you can store that more easily. So, when we consider the expression this, we could compute teaches with the course ID first and then join the result here. But this teaches times teaches natural join projection of course is expected to generate a larger result. How do I know? Statistical information. We can intuitively say, we can heuristically say, as human beings we can think, okay, right, because there are courses of several years in the teachers that exist, and there are naturally the course list is also very large, and so it will be quite some. But if I can take out only courses which is taught by instructors of music department, which is what this does, then that will not be very large, and then taking a join with the courses would just taking out the title would be appropriate, right. So, these are the different ways to generate alternate. So, the actual query evaluation plan will get generated by the query optimizer using these equivalence rules in a systematic manner, because you have to there is no kind of this is not known as to how many equivalent expressions would be there. Right. We can generate all of them by enumeration, right, apply all applicable equivalence rules on all sub expressions of all equivalent expressions found so far, and keep on generating that till you do not have anything new getting added to the set, right. Brute force method, which will obviously be kind of exponential and therefore very expensive, both in terms of time and in terms of space. Obviously, you are optimizing the query. So, the time taken to optimize cannot be so large that the benefit of optimization is lost or the query actually slows down, because you might be able to find a very optimal way to do the query, but the time you have taken to optimize is so large that your net effect is nulled. So, so often you you try to generate the optimized plan on the transformation rule and take different kinds of special case approach for the very common and widely used operations like selection, projection and join. So, if you think about that, then there are different ways you can handle things better. For example, space you can optimize by not duplicating the same expression. For example, we have the rule that E1 is same as commutativity, right. So, which means that I have a join and I have E1 here, I have E2 here, and they could be potentially large expressions. This is for the left hand side, and I will similarly have for the right hand side. E2 here and E1 here, right. But instead of making two copies of this for this alternate, I could just manage by doing kind of a multi tree pointers, right. So, the same sub expression may get generated multiple times. I can have a smart algorithm to detect duplicate sub expression and share only one copy. So, there are we do not have the opportunity to get into depth of these discussions, but I just wanted to give you a glimpse of what are the issues that are involved. And above all, time requirements are often drastically reduced by not generating all expressions, but using some kind of a dynamic programming. So, you keep on, so you as you keep on generating alternate expressions, you keep on tracking what is their current cost. So, you always have the best current cost option. So, you dynamically keep on checking as to how much, where all you need to improve on the equivalent expression, on which all will never give you a better expression, right, and keep on pruning that. I mean, typically the way the dynamic programming Tableau method works. So, that is to summarize, this is just a glimpse of optimization techniques for queries and generating a good evaluation plan for a given query. Thank you very much for your attention. We will meet in the next module.